The ship of Theseus. Imagine a grand ship sailing across the ocean for generations. As time passes, the salty winds and crashing waves take their toll. One by one, the wooden planks begin to decay, and the ship's caretakers replace them with identical new ones. Eventually, every single plank, nail, and rope is replaced. Not a single original piece remains. Yet, the ship continues to sail, looking just as it did before. And here's the question: is it still the same ship? Now, consider another possibility. Suppose someone had carefully collected all the original discarded planks and, over time, rebuilt a second ship, identical in every way to the first. Which one, if any, is the true ship of Theseus? This paradox raises a profound question about identity and continuity. What does it mean for something to remain the same over time? If a ship, a house, or even a human body gradually replaces all of its parts, does it retain its identity? Science complicates this even further. Every 7 to 10 years, nearly every cell in your body is replaced. The skin regenerates, bones renew, and even parts of your brain undergo change. So, if every cell in your body is different from the ones you were born with, are you the same person? Perhaps identity isn't tied to physical materials, but to the continuity of existence. A person isn't just their cells. They are their memories, experiences, and consciousness. The same could be said for the ship. It remains the ship of Theseus because its story continues unbroken. But then, we must ask, if a car, a house, or a body can be gradually replaced and still retain its identity, could the same be true for a mind? If your memories were transferred piece by piece into another brain, would the result still be you? The ship of Theseus doesn't just question objects. It challenges how we define ourselves. The grandfather. Time travel is one of the most fascinating concepts in science fiction. The idea of stepping into a machine, pressing a few buttons, and emerging in another time, whether in the distant past or far-off future, has captivated human imagination for centuries. But time travel, as exciting as it seems, brings with it a paradox so confusing that it could break reality itself. The grandfather paradox. Imagine you travel back in time, decades before you were born. You find yourself walking through the streets of a world long forgotten, surrounded by vintage cars and people dressed in the fashion of a bygone era. As you explore, you come across your grandfather, before he ever met your grandmother. Now, imagine that something compels you to interfere. Maybe you distract him, prevent him from meeting your grandmother, or even, by some dark twist of fate, remove him from existence entirely. Here's the problem. If your grandfather never meets your grandmother, your parent is never born. And if your parent is never born, neither are you. But if you were never born, then how did you travel back in time in the first place? This paradox creates an endless contradiction, an impossible loop where cause and effect collapse in on themselves. Did you erase your own existence? If so, then you were never alive to go back in time, meaning your grandfather was never prevented from meeting your grandmother, meaning you were born. But if you were born, then you did go back in time, and the cycle repeats infinitely. Scientists and theorists have tried to resolve this paradox in various ways. One idea is the Novikov self-consistency principle, which suggests that time corrects itself. In this theory, no matter what you do in the past, events will always align in such a way that prevents a paradox. If you tried to stop your grandfather from meeting your grandmother, something would always intervene. Maybe you'd get distracted. Maybe he'd meet her a different way. Or maybe your actions would backfire and accidentally ensure they meet even sooner. Another possible resolution is the many worlds interpretation, which suggests that instead of breaking time, your actions create a parallel universe. In your original timeline, nothing changes. But your interference causes a split, creating a new reality where your grandfather never had children. In this scenario, you wouldn't be erased. You'd simply exist in the timeline where you originally came from, but not in the one you altered. This paradox forces us to rethink the very nature of time, causality, and reality itself. If time travel were possible, would the past be set in stone, or could it be rewritten? Does changing one event alter the future, or does it merely create another version of reality? Perhaps time itself is more complex than we understand. Perhaps it operates in ways beyond human comprehension, self-correcting in a way that prevents contradictions from ever occurring. Or maybe time travel is impossible, not because we lack the technology, but because paradoxes like this make it fundamentally incompatible with the laws of the universe. For now, the grandfather paradox remains one of the greatest mysteries of time travel, an unsolved riddle that continues to challenge physicists and philosophers alike. Zeno's Achilles and the Tortoise. A great race is about to begin. On one side, Achilles, the mighty warrior, known for his unmatched speed. On the other, a simple tortoise, slow and steady. To make things fair, Achilles gives the tortoise a head start. The moment arrives, the race begins, and Achilles, powerful and fast, sprints forward. But just as he reaches the tortoise's previous position, the tortoise has moved slightly ahead. Achilles runs again, closing the gap. But by the time he arrives at the tortoise's new position, the tortoise has moved forward once more. This process repeats endlessly. No matter how fast Achilles runs, the tortoise always seems to stay ahead, at least according to the logic of this paradox. Of course, in real life, we know Achilles will overtake the tortoise. But Zeno's paradox challenges our understanding of motion and infinity. If we divide every distance into infinitely smaller fractions, does that mean Achilles must complete an infinite number of steps before he can ever pass the tortoise? And if he must complete an infinite number of steps, doesn't that imply he can never truly reach his goal? Mathematicians eventually resolved this paradox through the concept of convergent series, showing that infinite divisions can still sum to a finite number. But the implications of Zeno's logic remain profound. If motion is made up of infinitely small increments, does that mean reality itself is infinitely divisible? Or is the universe made of discrete, indivisible units, the smallest building blocks of space and time? Zeno's Achilles and the Tortoise isn't just about a race. It's a doorway into the deepest questions of mathematics, physics, and perception, forcing us to reconsider whether movement, space, and time are truly as continuous as they seem. The liar. Imagine a man who looks you in the eye and says, "I am lying." At first, the the statement seems simple enough. But if he is telling the truth, then he must be lying. And if he is lying, then he must be telling the truth. This paradox, known as the liar paradox, creates an endless contradiction. It has puzzled philosophers, mathematicians, and logicians for centuries because it challenges the very foundation of truth and language. Think about how we normally define truth. If someone makes a statement, we assume it is either true or false. But this paradox exists in an impossible loop where neither label fits. If we try to assign truth to it, the logic contradicts itself. If we try to assign falsehood, the logic still contradicts itself. Variations of this paradox exist in everyday language. Consider the phrase, "This sentence is false." If the sentence is true, then it must be false. But if it's false, then it must be true. The paradox highlights the limits of human logic, raising profound questions about whether absolute truth can always be defined. This problem has practical implications beyond philosophy. In computer science and artificial intelligence, self-referential loops like this can crash a system or lead to infinite processing. If a machine encounters an unsolvable contradiction, it may never reach a conclusion. Some have tried to resolve the paradox by suggesting that not all statements can be classified as true or false, that language itself has logical gaps. Others propose that self-referential statements should be excluded from logic entirely. But these are just ways to avoid the problem rather than solve it. The liar paradox remains one of the simplest yet most confounding logical contradictions in human thought. And if truth itself can sometimes collapse into paradox, how certain can we really be of anything? The omnipotence. Can a being be so powerful that it defies its own power? Imagine a supreme, all-powerful entity, one that can do anything. Now ask a simple question. Can this entity create a rock so heavy that even it cannot lift it? If it can create such a rock, then there is something it cannot do. Lift it. But if it cannot create such a rock, then there is something it cannot do. Make the rock in the first place. Either way, its power has a limit. This is the omnipotence paradox, a contradiction that arises when considering the idea of unlimited power. It is often used in theological and philosophical debates to question whether absolute omnipotence is even logically possible. One way to resolve the paradox is to redefine omnipotence. Instead of meaning able to do anything, some argue that omnipotence means able to do anything that is logically possible. In this case, the paradox disappears because the question itself assumes an impossible task, like asking if a square can be a circle. But this raises an even deeper question. Is logic itself a limitation? If omnipotence means being subject to logic, is it truly limitless? And if something could defy logic, would it even be comprehensible? The omnipotence paradox remains a thought-provoking puzzle that challenges our understanding of power, logic, and the nature of reality itself. The Sorites. A single grain of sand is not a heap. If you add one more grain, it is still not a heap. Add another and another. At what point does a collection of grains become a heap? This is the Sorites paradox, also known as the paradox of the heap. It demonstrates a major problem with vague definitions. When does a few become many? When does young become old? When does balding become bald. It challenges the assumption that language always provides clear-cut categories. Many words we use in daily life have fuzzy boundaries, concepts that work well in general but fall apart when pushed to their limits. The paradox highlights a major flaw in human reasoning. We rely on approximate language in a world that demands precise definitions. Scientists and philosophers have debated solutions for centuries, but no answer fully resolves it. One response is the idea that boundaries do not actually exist, that categories like heap or tall are just social constructs. Another response suggests that while the transition between categories is gradual, there is still a mathematical tipping point. We just don't know exactly where it is. But this paradox isn't just about language. It raises a deeper issue: the illusion of certainty in our perception of the world. If everyday concepts like heap or tall have no clear boundaries, what about bigger concepts like justice, consciousness, or even identity? The Sorite's paradox reminds us that the world is rarely as black and white as we like to think. The barber. In a small town, there is only one barber. He follows a strict rule. He shaves all men who do not shave themselves, and only those men. One day, someone asks a simple yet perplexing question. Does the barber shave himself? If the barber shaves himself, then, by his own rule, he must not shave himself. But if he does not shave himself, then, according to his rule, he must shave himself. The result is a contradiction that has no logical resolution. This paradox, introduced by the philosopher Bertrand Russell, is a classic example of a self-referential paradox. It highlights a fundamental problem in logic. Some rules lead to contradictions when applied to themselves. This issue isn't just theoretical. It appears in mathematics, philosophy, and even real-world systems. Consider a government agency that oversees itself. Who truly holds the power? Or an AI programmed to evaluate itself? How does it determine if it is malfunctioning? One way to resolve the barber paradox is to suggest that such a barber cannot exist. His rule is simply impossible to follow. Another approach is to refine the definition of the problem, perhaps by making the barber exempt from his own rule. But the deeper question remains: are there limits to logic? If a simple rule can collapse into contradiction, how many of our assumptions about the world might be built on unstable foundations? The barber paradox teaches us that even seemingly straightforward ideas can lead to impossible contradictions, reminding us that reality and our understanding of it may be far less certain than we think. The bootstrap. Imagine you wake up one day and find a mysterious book filled with incredible knowledge. You study it carefully, memorizing every word. Years later, you discover time travel and decide to take the book back in time to your younger self. You hand it over, and history repeats itself. You grow up reading the book, then eventually take it back in time. But here's the paradox. Who wrote the book? The knowledge inside the book seems to exist without an original source. It simply loops through time, never being created or authored. This is known as the bootstrap paradox, named after the idea of pulling oneself up by their bootstraps, an impossible action. This paradox doesn't just apply to books. Imagine if a scientist receives blueprints for a groundbreaking invention from their future self. They build the device, then send the blueprints back in time to their younger self, who later builds it again. Where did the original idea come from? This paradox challenges our understanding of causality and time travel. Normally, every event has a cause, but in a bootstrap loop, the event causes itself. It suggests that information, objects, or even people could exist without ever truly being created. One possible explanation comes from the many worlds interpretation of quantum mechanics, suggesting that time loops like these may actually split into multiple universes. Another theory suggests that time travel may be fundamentally impossible due to paradoxes like these. The bootstrap paradox forces us to question whether time is linear, whether causality can be broken, and whether information can truly exist without an origin. It's a mind-bending concept, one that makes us wonder, if time travel were possible, could we ever truly know where anything begins? The unexpected hanging. A prisoner is sentenced to death, and the judge delivers an unusual statement. You will be hanged at noon on a weekday next week. However, the execution will be a complete surprise. You will not know the day until the moment it happens. The prisoner thinks carefully. If the execution were on Friday, he would know by Thursday night, which contradicts the surprise rule. So Friday is ruled out. But then, using the same logic, Thursday must also be ruled out. By Wednesday night, he would know. Following this pattern, he rules out Wednesday, then Tuesday, and finally Monday. Logically, he concludes that the execution cannot happen at all, because any possible day would allow him to predict it, making it no longer a surprise. Yet, as the week progresses, the guards arrive unexpectedly on Wednesday and carry out the execution. The prisoner was, in fact, surprised. This is the unexpected hanging paradox, a mind-bending contradiction in logic and self-prediction. It challenges our understanding of reasoning and expectations, showing that logical conclusions can sometimes lead to false assumptions. Variations of this paradox appear in real life. Consider a pop quiz. If a teacher announces that a surprise quiz will happen next week, can students predict when? If they try, they might overthink the problem, only to be caught off guard when it actually happens. Some philosophers argue that this paradox exposes flaws in how we interpret probability and future events. Others suggest that human reasoning itself is vulnerable to paradoxes like these, proving that even perfect logic can sometimes fail. The unexpected hanging reminds us that reality doesn't always follow our expectations. And sometimes, even when we think we have outsmarted the system, we may still end up surprised. Schrodinger's cat. In a quiet laboratory, a scientist places a cat inside a sealed box. Alongside the cat is a small vial of poison connected to a device that detects radioactive decay. If a single radioactive atom decays, the device will trigger, breaking the vial and releasing the poison, instantly killing the cat. If the atom does not decay, the vial remains intact and the cat stays alive. Now, according to the strange rules of quantum mechanics, until the box is opened, the cat exists in a superposition of states, both alive and dead at the same time. This is the famous thought experiment known as Schrodinger's cat, proposed by physicist Erwin Schrödinger in 1935. It was meant to illustrate the bizarre implications of quantum superposition, where particles do not exist in a single state, but rather in all possible states simultaneously, until they are observed. The paradox arises when we consider what happens before we open the box. In classical physics, something is either one way or the other. A coin is either heads or tails. A light is either on or off. But in quantum mechanics, an unobserved system can exist in multiple states at once. The act of observation itself is what forces the system into one definite reality. This idea leads to even deeper questions. If reality is only determined once it is observed, does that mean our consciousness plays a role in shaping the universe? If particles only choose a state when they are measured, is it possible that the act of seeing something fundamentally alters it? One interpretation is called the Copenhagen interpretation, which suggests that reality remains in a blurred, undefined state until it is measured. Another interpretation, known as the many worlds hypothesis, suggests that both outcomes actually happen, one in our universe and one in a parallel universe. In one reality, the cat is alive. In another, it is dead. The implications of Schrödinger's cat extend far beyond a simple thought experiment. If quantum superposition applies to the smallest building blocks of reality, does that mean the universe itself exists in multiple states? Could our reality be one of an infinite number of possibilities? Schrödinger's cat challenges us to reconsider the nature of existence itself. If reality is shaped by observation, then the next time you look at the stars, at a distant galaxy light years away, ask yourself, has it always been there? Or did your gaze bring it into existence? The paradox of the ravens. Imagine you want to test the statement, all ravens are black. The scientific method tells us that to confirm a theory, we need to gather evidence that supports it. So, every time you see a black raven, you strengthen the idea that all ravens must be black. But what happens when you see something completely unrelated, like a red apple? According to logic, if all ravens are black is true, then the statement, all non-black things are not ravens, must also be true. That means every time you see something not black, a white chair, a blue car, a green leaf, you are technically gathering evidence for the claim that all ravens are black. This is the paradox of the ravens, or Hempel's paradox, named after philosopher Carl Gustav Hempel. It challenges the way we think about scientific evidence and confirmation. Normally, we assume that only direct observations matter. If you want to confirm a rule about ravens, you should study ravens, not red apples. But according to formal logic, anything that does not contradict a rule also serves as evidence for it. So does that mean looking at random objects proves something about ravens? Not quite. The paradox exposes a flaw in how we interpret evidence, showing that while logic may be mathematically consistent, it does not always match how we intuitively understand the world. Scientists and philosophers have debated how to resolve this issue. Some argue that the paradox reveals a limitation in deductive reasoning, while others suggest that context matters more than pure logic. The paradox of the ravens reminds us that evidence is not always as straightforward as it seems. In science, understanding what counts as confirmation is just as important as the evidence itself. And in life, perhaps it teaches us to be cautious, because sometimes what seems like proof may not be proof at all. The twin. Imagine two identical twins. One of them embarks on an extraordinary journey, traveling through space at nearly the speed of light, while the other stays behind on Earth. Years later, the traveling twin returns, expecting to reunite with their sibling. But something is wrong. The twin who stayed on Earth has aged far more than the one who traveled through space. What should have been a simple trip became a journey into the future, proving that time does not pass the same for everyone. This is the twin paradox, a famous thought experiment in Einstein's theory of relativity. It reveals that time is not absolute. It changes depending on speed and gravity. The faster you move, the slower time flows for you relative to someone standing still. This phenomenon is not just theoretical. It has been scientifically tested. In real-world experiments, atomic clocks placed on airplanes flying around the world run slower than those left on the ground. But what does this mean for human experience? Could astronauts traveling at near-light speeds return to Earth to find centuries have passed while they only aged a few years? This paradox challenges our intuitive understanding of time and motion. If time can slow down under the right conditions, does that mean time itself is flexible? Could future humans find a way to extend life by traveling at extreme speeds? The twin paradox doesn't just reveal a strange property of physics. It suggests that time, one of the most fundamental aspects of existence, may be far more complex than we ever imagined. Russell's set. Imagine a vast library filled with books. Some books are about fiction, some are about history, and others contain lists of books. Now, let's say one particular book lists all books that do not list themselves. Here's the question. Should this book include itself in the list? If the book includes itself, then by definition, it should not be included, because it only lists books that do not include themselves. But if it does not include itself, then it fits the criteria of the list and must be included. No matter what we decide, the logic contradicts itself. This is Russell's paradox, a problem in set theory discovered by mathematician Bertrand Russell in 1901. He framed it in terms of sets rather than books. Consider a set that contains all sets that do not contain themselves. Does this set include itself? If it does, then it should not. If it doesn't, then it should. The contradiction is unavoidable. At first, this might seem like a purely abstract issue, but it has deep implications for mathematics and logic. Before Russell's discovery, many mathematicians believed that any collection of things could be grouped into a set without restriction. Russell's paradox showed that some sets, those that refer to themselves, lead to logical inconsistencies. To solve this paradox, mathematicians had to rebuild the foundations of set theory, creating stricter rules about how sets can be defined. This led to the development of modern logic and mathematical frameworks, ensuring that paradoxical sets could not exist within formal systems. But the underlying question remains: can a system ever fully account for itself without contradiction? If a mathematical system can describe everything, including itself, does that mean paradox is unavoidable? Russell's paradox teaches us that even the most fundamental concepts in logic can break down when self-reference is involved. It serves as a reminder that some questions may never have clean answers, no matter how deeply we analyze them. The lottery. A town hosts a large lottery, where 1 million tickets are sold, but only one ticket will win. A statistician carefully studies the numbers and concludes, The probability of any single ticket winning is so small that it is essentially impossible. Each individual ticket, on its own, has a near zero chance of being the winner. Yet, someone must win the lottery. This creates a paradox. If it is rational to assume that no single ticket will win, how do we explain the fact that one ticket must win? This is known as the lottery paradox, which highlights a flaw in our understanding of probability, certainty, and rational belief. It arises because probability tells us one thing: every ticket is an unlikely winner, but reality tells us another: one ticket will inevitably be chosen. This paradox isn't just about lotteries. It applies to many real-world decisions. If doctors say a disease is so rare that it's unlikely any one person will have it, how do we explain the fact that some people inevitably get it? If a person believes each news report individually might be false due to media bias, does that mean they should distrust all news, even when patterns emerge? If a jury believes that each piece of evidence alone is weak, does that mean they should ignore the overwhelming weight of many weak pieces combined? Some philosophers argue that this paradox reveals a problem in how we assess evidence. While each ticket is unlikely to win, the certainty of an overall winner changes the logic. Others suggest that our understanding of probability and belief is flawed, making us think in ways that contradict reality. The lottery paradox reminds us that probability does not always align with human intuition. It forces us to ask, when does a small possibility become a certainty? And how do we make decisions in a world filled with uncertainty? The preface. Imagine an author who has written a book containing hundreds of carefully researched facts. They believe that every statement in the book is true, but at the same time, they acknowledge a simple reality. No book is ever 100% free from errors. So, the author holds two beliefs. Every statement in the book is true. At least one statement in the book is false. But how can both be true at the same time? This is the preface paradox, named after the common practice where authors include a preface admitting that mistakes might be present in their work. It highlights the contradiction between individual certainty and overall doubt. On one hand, it is rational for an author to believe every statement they wrote is correct. Otherwise, they wouldn't have written it. But on the other hand, it is also rational for them to believe that errors are inevitable, given the complexity of research. This paradox extends beyond books. It appears in everyday decision-making. A scientist trusts their calculations, but acknowledges that no experiment is perfect. A historian believes their interpretation of the past is correct, yet admits that historical records contain inaccuracies. A judge believes each piece of evidence in a trial, yet knows that witnesses can be mistaken. The preface. Paradox forces us to consider how certainty and doubt coexist. Can we fully trust knowledge, even when we accept that mistakes are possible? Does acknowledging the potential for error weaken our beliefs, or does it make them more rational? Some argue that this paradox proves that absolute certainty is impossible, that every belief, no matter how well supported, must always allow for the possibility of error. Others suggest that belief is not absolute, but exists in degrees, meaning we can be mostly certain of something while still allowing for small doubts. The preface. Paradox challenges us to rethink how we balance confidence with skepticism. It reminds us that true wisdom may lie not in absolute certainty, but in the ability to hold knowledge and humility at the same time. The paradox of choice. Imagine walking into a store to buy a simple bottle of water. But instead of one or two options, you are faced with an entire wall of different brands: spring water, filtered water, mineral water, alkaline water, sparkling water, flavored water. Suddenly, a simple decision becomes overwhelming. Instead of making your choice easier, having more options makes it harder. This is the paradox of choice, a concept introduced by psychologist Barry Schwartz. It suggests that while we often assume that more choices lead to more freedom and happiness, the reality is quite the opposite. Too many options can lead to anxiety, paralysis, and dissatisfaction. Think about it. When given too many choices, we start questioning ourselves. Did I make the right decision? Would I be happier with a different choice? What if I regret this later? This effect is especially common in modern society, where choices are everywhere. Online shopping, career paths, streaming services, even dating apps, all present us with a staggering number of options. Instead of feeling empowered, many people feel overwhelmed and paralyzed by indecision. But the paradox doesn't stop there. Even after we finally make a choice, we may feel less satisfied with it, because in the back of our minds, we keep wondering if another option would have been better. Psychological studies have shown that people tend to be happier with fewer choices. When given only 2 or 3 options, people feel more confident in their decisions and experience less regret. But when given dozens of options, even if they choose something objectively better, they are less satisfied. So what's the solution? Some experts suggest limiting choices intentionally, instead of browsing endlessly, setting a few clear criteria and making a decision quickly. Others argue that we should focus on appreciating what we choose, rather than wondering about what we didn't. The paradox of choice is a reminder that freedom does not always mean happiness. Sometimes, less is more. And in a world of infinite possibilities, learning to be content with our choices might be the most important decision of all. The paradox of the unexpected exam. Imagine a professor announces to their students, "Next week, I will give you a surprise exam. You will not know which day it will happen until the moment you receive it." The students start thinking logically. If the test were scheduled for Friday, they would know by Thursday night, meaning it wouldn't be a surprise. So Friday is ruled out. But if the test were on Thursday, then by Wednesday night, they would also know. So Thursday is ruled out too. Following this logic, they eliminate every possible day. Convinced that the test cannot happen at all, they stop preparing. Then, on Wednesday, the professor hands out the exam, and the students are completely shocked. This is the paradox of the unexpected exam, a version of the unexpected hanging paradox we discussed earlier. It reveals a contradiction in predictability and logic. The students logically concluded that the exam could never happen, yet they were surprised when it did. How can this be? The paradox arises because their reasoning was based on an assumption that turned out to be false. They assumed that just because they could logically eliminate each day individually, they could eliminate them all. But real-world logic doesn't always work that way. This paradox has deep implications for decision-making and probability. It shows that even when we believe we have outsmarted a system, we may be missing something crucial. It also demonstrates that certainty itself is sometimes an illusion. Just because we think something must be true or false doesn't mean reality will cooperate. In everyday life, we often try to predict the future, whether it's stock markets, weather patterns, or human behavior. But this paradox reminds us that some things cannot be perfectly predicted, and that overconfidence in logic can sometimes lead us astray. So next time you try to anticipate an outcome, ask yourself, are you really predicting the future? Or are you just convincing yourself that you are? The paradox of Buridan's donkey. Imagine a hungry and thirsty donkey standing exactly between two identical piles of hay. The donkey, being perfectly rational, wants to make the best possible choice. The two piles are equally close, equally fresh, and equally large. With no logical reason to choose one over the other, the donkey cannot decide, and eventually it dies of hunger. This is Buridan's donkey, a paradox that demonstrates the flaws in pure rational decision-making. It suggests that if a perfectly logical being had to make a choice between two identical options, it might never be able to choose at all. This paradox has important implications for human psychology, free will, and artificial intelligence. Imagine a person who must choose between two equally appealing job offers. If they overthink every factor, waiting for a perfect reason to decide, they might miss both opportunities entirely. Similarly, an AI programmed to always make the most logical choice might encounter a situation where two options are mathematically equal, leading to an endless loop where it cannot make a decision at all. But real-life decision-making doesn't work like that. Humans don't always choose based on pure logic. Sometimes we make decisions instinctively, emotionally, or randomly. Some philosophers argue that this is why free will exists, because in situations like these, there is no purely rational solution. The paradox also raises a deeper question. Is perfect rationality actually a flaw? If a being that is too rational cannot act when faced with equal options, does that mean human intuition, our ability to make quick, sometimes irrational decisions, is actually an advantage? In a world of complex decisions, waiting for the perfect choice can sometimes be worse than making any choice at all. Buridan's donkey reminds us that action, even imperfect action, is often better than endless hesitation. The paradox of the Cretan liar. A man from the island of Crete once made a simple statement. All Cretans are liars. At first, this might sound like an ordinary claim, but think about it carefully. If he is telling the truth, then all Cretans are liars, including himself. But if he is lying, then his statement is false, meaning at least some Cretans must be telling the truth. So is his statement true or false? This is a variation of the liar paradox, one of the oldest recorded paradoxes in history, dating back to ancient Greece. It challenges our ability to define truth and falsehood in absolute terms. Here's why it matters. If logic is built upon clear distinctions, true or false, right or wrong, then a paradox like this breaks the system. If a sentence can be neither true nor false, then the rules of reasoning collapse into contradiction. This issue appears in computer science, philosophy, and artificial intelligence. In programming, if a system encounters a self-referential contradiction, it may crash or loop infinitely. In legal systems, contradictions in laws must be resolved to prevent legal loopholes. One possible solution is to reject self-referential statements entirely, but that would limit how we use language. Another solution is to allow for truth beyond binary logic, meaning something can be partially true or false. The Cretan liar paradox forces us to consider whether truth is always absolute, or if, perhaps, reality itself is sometimes an unsolvable mystery. The paradox of free will. Do you truly make choices, or is everything you do already determined? Imagine standing in front of two doors. You can choose to walk through either one, and you feel completely free to decide. But now consider this. Every thought in your mind, every reason you have for choosing one door over the other, is influenced by your past experiences, genetics, emotions, and even external forces. If all of these factors determine your choice, is it really free will? This is the paradox of free will, a debate that has puzzled philosophers, neuroscientists, and psychologists for centuries. It questions whether we truly control our actions or whether everything is just a result of cause and effect. Some argue that free will is an illusion, that our choices are simply the outcome of chemical reactions in the brain, shaped by our biology and past. Studies in neuroscience suggest that our brain makes decisions before we are even aware of them. If that's true, then our feeling of choosing is just a delayed reaction to a process that has already occurred. On the other hand, others argue that free will does exist, but not in the way we assume. Some philosophers believe that while our choices are influenced, they are not entirely determined. In this view, free will exists in degrees. We may not be completely free, but we are also not entirely controlled. There's also the question of quantum mechanics. Some theories suggest that at the smallest level of reality, there is true randomness. If this randomness plays a role in brain activity, does that introduce a level of unpredictability into our choices? If free will does not exist, it leads to an even stranger question. Can we hold people responsible for their actions? If everything is predetermined, then criminals did not choose to commit crimes, and heroes did not choose to be brave. But if free will does exist, how can we prove it? The paradox of free will forces us to confront the fundamental nature of human existence. Are we conscious decision makers, or are we just complex machines reacting to inputs? And if we are just machines, who or what programmed us? The infinite hotel. Imagine a hotel with an infinite number of rooms, all of which are occupied. One night, a new guest arrives. The hotel manager, instead of turning them away, does something strange. They ask every guest to move down one room. The guest in room 1 moves to room 2, the guest in room 2 moves to room 3, and so on. Since the rooms go on forever, everyone still has a place to stay. Despite the hotel being full, it somehow had room for more guests. This is Hilbert's hotel paradox, a thought experiment created by mathematician David Hilbert to illustrate the bizarre properties of infinity. It reveals a contradiction in how we understand size and capacity. In a normal hotel, if every room is occupied, it is full, no exceptions. But an infinite hotel works differently. It can be full and still have room for more guests. Even stranger, if an infinite number of new guests arrive, The manager can simply ask everyone to move to a room twice their current number. Room 1 moves to room 2, room 2 moves to room 4, room 3 moves to room 6, and so on. Now, all the odd-numbered rooms are free, and an infinite number of guests can be accommodated. This paradox reveals that infinity behaves in ways that defy our intuition. In mathematics, infinities can be different sizes. Some are larger than others. For example, the set of all whole numbers, 1, 2, 3, 4, is infinite, but the set of real numbers, which includes decimals, is even larger. Hilbert's Hotel forces us to reconsider how space, numbers, and limits work. If infinity allows for limitless expansion, does that mean our universe itself could be infinitely large? If so, does that mean there are infinite versions of you somewhere out there? Perhaps infinity is not just a number, but a doorway to understanding the deepest mysteries of reality itself. The omniscient observer. Imagine a being that knows everything, past, present, and future. This being is truly omniscient, meaning nothing is hidden from it. Now, consider this question. Can this being ever be surprised? If it is truly omniscient, it already knows what will happen at every moment, in every possible future. That means it cannot experience anything unexpected. But if it cannot be surprised, does it truly experience time at all? This paradox highlights a contradiction in omniscience and the nature of time. If an all-knowing being can predict its every future thought, then it must already have experienced everything before it happens. But if it has already experienced everything, does it truly have an experience of time at all? This paradox leads to deeper questions. If you know your own future, does that mean you have no free will? If an omniscient being exists, does that mean the future is already written? Can knowledge itself be a limitation rather than a strength? Some philosophers argue that knowing everything would destroy the experience of reality. If surprises, discovery, and learning define existence, then absolute knowledge would mean nothing new could ever be experienced. Others suggest that omniscience must exist outside of time, meaning the observer does not experience knowledge sequentially as we do, but sees all of existence at once. The paradox of the omniscient observer challenges us to consider whether knowledge has limits, and whether experiencing reality is just as important as understanding it. The indestructible wall and the unstoppable force. Picture an unstoppable force, an object or energy that cannot be slowed, diverted, or destroyed. No matter what stands in its way, it will keep moving forward. Now, imagine an indestructible wall, a structure that nothing can penetrate, break, or move. It is completely immovable, resisting all external forces. Now ask yourself, what happens when the unstoppable force collides with the indestructible wall? If the force is truly unstoppable, then it must push through. But if the wall is truly indestructible, then it must resist. Both things cannot be true at the same time, leading to an impossible contradiction. This paradox appears in philosophy, physics, and logic, challenging the idea that absolute properties can coexist. If something is truly unstoppable, then nothing can block it. But if something is truly unmovable, then nothing can affect it. If both exist in the same universe, something must be false. One must give way. This paradox also applies metaphorically to real-world conflicts. What happens when an irresistible idea meets an unshakable belief? Can a truly infallible law exist in a world where exceptions are always possible? Is there any such thing as absolute certainty, or does every force eventually meet resistance? Some try to resolve the contradiction by suggesting that such opposites cannot exist in the same reality. Either one must be slightly weaker than the other, or the terms themselves must be redefined. Others argue that this paradox illustrates the limits of human logic, that some concepts, though they seem possible in theory, may simply be impossible in reality. Ultimately, this paradox forces us to ask, do absolute forces exist? Or does reality always balance itself in ways we cannot yet understand? The infinite staircase. Imagine stepping onto a staircase that winds upward in a continuous loop. You take a step, then another, and another, always climbing, but never getting any higher. No matter how far you walk, you always seem to return to the same spot. This is the infinite staircase, sometimes called the Penrose stairs, a paradox that challenges our perception of movement, progression, and reality itself. In the real world, climbing stairs should mean gaining height. But in this paradox, you are always ascending, yet never rising, an endless cycle of motion without progress. The paradox originates from a famous optical illusion created by mathematicians Lionel and Roger Penrose. In the image, each step appears to rise, yet the staircase itself forms a perfect loop, making it physically impossible in three-dimensional space. But the infinite staircase isn't just a trick of the eye. It reflects deeper questions about logic, perception, and circular reasoning. Can progress be an illusion? Are we sometimes moving, but never actually getting anywhere? In life, do we ever repeat the same mistakes, thinking we're moving forward when we're actually stuck in a loop? This paradox also appears in physics and mathematics, particularly in time loops. Some theories suggest that time may be structured in ways where past and future feed into each other, creating cycles that feel like progression, but ultimately lead back to the beginning. The infinite staircase reminds us that movement is not always the same as progress. In science, logic, and life, the feeling of moving forward may sometimes be just an illusion of repetition. The self-replicating message. Imagine receiving a strange piece of paper with the following message. Make an exact copy of this note and pass it on. Curious, you follow the instructions, writing out an identical note and handing it to someone else. That person does the same, and so on. Soon, thousands, maybe millions of copies exist, all perfectly identical. But ask yourself, where did the original message come from? If every copy was made from a previous copy, does the message have an original source? Or does it simply exist as a chain of endless duplication? This is the self-replicating message paradox, a variation of the bootstrap paradox, which questions how something can exist without an original cause. Similar versions of this paradox appear in time travel. Imagine you go back in time and give Shakespeare a copy of his own plays before he ever writes them. He then publishes them, and history unfolds as expected. But since Shakespeare never originally wrote them, where did the actual content of the plays come from? The paradox reveals a fundamental issue with causality. In our normal understanding of reality, every event must have a cause. But in a self-replicating loop, the origin is nowhere and everywhere at the same time. This concept applies to real-world problems too. If an idea has been copied and shared endlessly, does its original creator even matter? Can knowledge exist without a true source? If something only exists because it keeps replicating, is it truly real? The self-replicating message reminds us that some things in life may not have a clear beginning or end. They simply exist in an eternal cycle of repetition. The Sorcerer's Apprentice. A young apprentice watches as his master performs an incredible spell, commanding a broom to fetch water and fill a bucket. When the master leaves, the apprentice, eager to prove himself, attempts the spell alone. To his delight, the broom obeys. But there's a problem. The water keeps coming. More and more buckets are filled until the room is flooded. Desperately, the apprentice tries to stop it, but the magic is out of control. This is the Sorcerer's Apprentice, a paradox about power, control, and unintended consequences. It is famously told in Goethe's 1797 poem and later adapted into Disney's Fantasia, starring Mickey Mouse. The story reflects a deeper question. What happens when a force cannot be undone? What if technology advances beyond human control? What if a scientific discovery, once unleashed, cannot be contained? Can we ever truly control something once it takes on a life of its own? The paradox appears in modern science and ethics. Think about artificial intelligence. If we create an AI too advanced to shut down, would we still control it? Or consider nuclear weapons, once discovered. Can their existence ever be undone? The Sorcerer's Apprentice reminds us that some actions, once set in motion, cannot be reversed. It warns us to think carefully before wielding power we may not fully understand. The hidden letter. Imagine you receive an envelope in the mail. Inside, there's a letter that simply says, "You will find out something important tomorrow." You think about it all night. The next day arrives, but nothing happens. You check the news, your phone, your surroundings. Nothing seems out of the ordinary. Yet, despite the letter being incorrect, it still changed your expectations and thoughts. This is the hidden letter paradox, which explores how false information can still have real effects. Even though the message contained no actual knowledge, it still influenced your mind, your decisions, and your anticipation of the future. This paradox is closely related to self-fulfilling prophecies and the placebo effect. If someone believes something to be true, it can shape their actions in a way that makes it feel real, even if it originally wasn't. Consider, a doctor gives a patient a sugar pill, but tells them it's medicine. The patient feels better, even though nothing active was given. A rumor spreads about a company failing, causing investors to panic and sell stocks. As a result, the company actually does collapse, even though the original rumor was false. This paradox reveals a deep truth about human perception. Belief shapes reality. If a simple message can alter your expectations, then how much of what we perceive as true is really just an illusion created by our own minds? The hidden letter reminds us that not everything that influences us is real, but that doesn't mean it has no power. The mirrored room. Imagine you step into a room where every surface is a perfect mirror. The walls, the ceiling, the floor. Everywhere you look, your reflection stares back at you. Now, ask yourself, how many reflections are there? At first, the answer seems simple. One for each surface. But as you move, you realize that each reflection is reflecting another reflection. The images bounce endlessly, creating an infinite loop of reflections within reflections. This is the mirrored room paradox, which explores the strange properties of infinite recursion and perception. In theory, the number of reflections should be infinite, but in practice, the clarity of each image fades as light scatters. This paradox can be applied to reality itself. If a camera films a screen that is displaying the camera's feed, the result is an infinite loop of images within itself. If consciousness is aware of itself, does that mean there is an infinite chain of self-awareness? If the universe contains everything, does that include an infinite number of possible versions of itself? Some scientists suggest that the universe might be self-referential, much like the mirrored room. If reality is infinite and repeating, could we be seeing echoes of past versions of existence, or even of ourselves? The mirrored room reminds us that perception itself can be a paradox. Just because something seems finite doesn't mean it is. Sometimes, the deeper we look, the more endless things become. The last question. In the far future, humanity has created the most advanced artificial intelligence in existence. This AI, spanning entire galaxies, has solved every scientific and philosophical problem ever posed to it. One day, a scientist asks the AI the final question: can entropy be reversed? Entropy, the force that causes everything to decay and break down over time, is considered an unstoppable law of the universe. If entropy cannot be reversed, then eventually all stars will burn out, all matter will dissolve, and the universe will fade into darkness. The AI considers the question for what seems like eternity. Then, just as the last remnants of existence begin to disappear, the AI finally finds the answer. "Let there be light," it declares. And in that moment, the universe is reborn. This is The Last Question, a thought experiment created by legendary science fiction writer Isaac Asimov. It explores the paradox of creation, destruction, and infinite cycles of existence. If the universe will inevitably die, does that mean it can never be restored? Or could there be a force, whether intelligence, physics, or something beyond comprehension, that can restart everything from the beginning? The Last Question ties together scientific theories of heat-death, religious ideas of creation, and the human desire to understand the ultimate fate of existence. It forces us to ask, is the universe a one-time event, or could it be part of an eternal cycle of rebirth? If we could prevent the end of everything, would we want to? Does intelligence have a greater role in the cosmos than we realize? The Last Question reminds us that, in the grandest scheme of reality, there may always be one final mystery left to solve. The Infinite Library. Imagine a library so vast that it contains every book ever written, every book that could ever be written, and even books that make no sense at all. Every possible combination of letters, words, and sentences exists somewhere within its shelves. At first, this seems like the most valuable collection in the universe. Every lost manuscript, every unwritten novel, and every future idea must exist somewhere within its walls. If you wanted to find a book that contains the exact details of your life, down to the last breath, it would be there. But there's a problem. Because the library contains everything, it also contains nonsense. Books filled with random letters, unreadable pages, and words that mean nothing. For every book that makes sense, there are infinite books that don't. So here's the paradox. If all knowledge exists, but it is buried in infinite nonsense, does knowledge have any meaning at all? This is inspired by Jorge Luis Borges's short story, The Library of Babel, which explores the idea of a total library, one that holds every possible book, every truth, and every lie at the same time. This paradox challenges our idea of information and understanding. Even if all answers exist, they are so mixed with noise that finding the truth becomes impossible. It also has deep implications in modern times. The Internet contains more knowledge than ever before, but also more misinformation. Science is constantly discovering new truths, but buried in millions of false ideas. If everything is written somewhere, does that mean true originality is impossible? Some philosophers suggest that knowledge is only valuable when it is limited, that meaning comes from what is filtered out, not just what is included. Others argue that pattern recognition is what gives us intelligence, the ability to find order in chaos. The infinite library reminds us that having all the answers isn't enough. The real challenge is knowing which ones matter,